In this lecture, we will discuss how the linked list class is implemented. Just as we did with the myArrayList class, to avoid any ambiguities with the built-in library class, we're going to call our class myLinkedList. And we'll implement it just like the linked list class, where we use a doubly linked list. This means that we're going to have to maintain references to both ends of the list, the beginning of the list and the end of the list. We'll need three classes to make this implementation work. We'll first need the myLinkedList class itself. This is going to contain the links to both ends. It's going to contain the size of our list. It'll also contain several methods that we need for the linked list, such as adding and removing nodes. We're also going to need the node class. So this is likely to be a private nested class. So the node class here is going to contain the data and the links to the previous nodes and the next nodes, and it's also going to contain the appropriate constructor for the node class. Finally, we're going to need the linked list iterator class. So this is just like the array list iterator class that we had before with the array list class previously. And this class is going to take care of this notion of the current position. And this is also going to be a private inner class. Now this will implement the iterator interface, so it's going to give us implementations for the next, the has next, and the remove methods. Now since the iterator classes store this reference to a current node, and we've already mentioned that the end marker is a valid position, so to say we're at the end of the list is valid, it actually makes sense to just say we'll create an extra node at the end of the list that represents the end marker. We can also do the same thing at the beginning of the list to represent a beginning marker. So what we're going to do is we're going to add two extra nodes, one at the beginning and one at the end, to actually say this is the beginning and the end of the list respectively. So these extra nodes are sometimes called sentinel nodes. Specifically, the node that's at the front is known as the header node, and the node that's at the end of the list is known as the tail node. The nice thing about using these sentinel nodes is that it helps simplify how we code all the operations because we remove several of the special cases. Let me give you an example. Let's say we don't use a header node and we want to remove the first node from our linked list. This now becomes a special case because we're going to have to change the list's link to the first node. If we had the header node there, the list first link would always point to that header node. But since it's not there, we're going to have to change that every single time. And likewise, if we're going to remove that first node in our list, we have to have access to the previous node. So without it, we're going to have to do something special with it. But if we had this header node in there, we can just refer to that header node in order to make the changes. Here's an example of a linked list with header and tail nodes. So notice that we have our header node right here, and our tail node is right here. And all the main nodes are between the header and tail. So in this case, we have two nodes in our linked list. So we have our first link point to the header, and we have our last link point to the tail node. So then we can use these as the starting points with our iterator to traverse through the list backwards and forwards. And here is just an example of an empty linked list. So we still have two nodes. We'll have the header and tail nodes. It's just there's nothing in between them. So whenever we need to add nodes, we would know to either start the head or at the tail, depending on how the implementation is done. And we can just add nodes in between the header and tail nodes. Let's now take a look at the implementation for the myLinkedList class. You're going to see some similarities with the myArrayList class, but a lot of the methods are now being implemented using the linked list instead of the array. So we can take a look that we have public class myLinkedList implements iterable, and then we have the any type so we can specify the data type whenever we actually create an object of the class. We see we still have the size variable, so we know how many things are in the list, but we have a couple new things as well. So we have mod count. We'll talk a little bit about this very shortly, but we use this to keep track of the number of changes since the linked list is created. And this helps us out with the iterators because we need to know if a change has been made to the list before using an iterator again. And we also create nodes for the begin marker and end marker that we just talked about previously. So this will give us our starting point and ending point for our linked list. We also have our nested class here for node, which is going to contain a data field. It's also going to contain a link for the next node and the previous node in our list. And then we have a constructor to initialize the variables for a particular node. And then we have mostly the same methods that we've had before. It's just now we're implementing them with the list. So we have our default constructor that's going to call doClear. We have a clear method that would pretty much clear the contents of a linked list, which also calls doClear. So let's see how doClear works. So we're resetting the beginning and end marker. So we're just making new nodes. And then we're setting begin marker next to the end marker. So all the other nodes that were in the list will no longer be accessible. So the Java garbage collector will take care of that for us later. We reinitialize the value of size to 0, and we increment our mod count. And then we have our size method, which gives us the current size. We can check to see if the list is empty, so we just check to see if the size is 0. We have our add method, which works just like the one from the myArrayList class, where we're going to add an element at the end of the list, or add an item. And then our add method, well, we're going to use the add before method to do that. So we're going to get a particular node. So this is going to take care of the add implementation for us. So we get the node at a particular spot, and then we're going to say we're going to add right before there. So this is actually going to take care of adding at the beginning of the list is how we're going to do this. We have our get method right here. And then that's going to get a particular node. We're going to get the data for a specific node. We have our set method right here. So that is going to allow us to get a specific node. And then we're going to change the value of that particular node, or at least the data field for that particular node. And we will return the old value of that data. We have our remove method. So we're going to call the corresponding remove method for getting a particular node at that index. Here's our implementation for add before. So what we're going to do is we're going to create a new node. We're going to call it new node, and that's going to have the data that we want in there. And then all we're going to do is just set new node previous next to the new node, and then p.prev is going to be the new node. So we're inserting the new node right at the exact spot that's specified for our node here. So I think before I might have said that we're inserting at the beginning, and I don't think that's always true. Let's go back just to make sure. Okay, so if we just have add with no specification, we're going to add it at the very end of the list. And then here we specify the index. Okay, yeah, so we're saying we're adding a specific index is what's going on here. Yeah, so we're not always adding at the very beginning, but we're going to add before a particular node. That's what's going on there. All right, so then we'll move back down here. So once we've added the particular node and established the links, we'll increment both the size and mod count. And then we have our remove method. So if we're going to remove a particular node, we need to change the next and previous links that are next to that particular node. And that's what we're doing here, just to make sure that we can no longer access node P. We decrease the size and we increment mod count. And we also return the data in that particular node, because once this is done, we're not going to be able to access that node anymore. And then we have our get node method, which is going to call get node for specific index. So we pass the index, and we can say we want this index and this particular range, which is the entire list. Get node in general is going to look at a particular index, and given a lower and upper bound, we can find that particular node. And notice that these particular methods are private, and that's intentional because we don't want these methods to be called outside of the class. We have other methods that will take care of it for us. So like the remove method here, that's a public method. We can call this, and it's going to call the corresponding remove method. So even though we have a bunch of different versions of add and removes,
though only a few of those methods can actually be called in some client class. The rest of these are private and done internally. But let's get back to this getNode implementation. So we have a reference variable for a node. We check our bounds to make sure it's valid. If not, then we need to throw an index out of bound exception. We then check to see, where is this index? Is it on the bottom half of the list or the top half? If it's in the bottom half, then we're going to start at the beginning of our list and search until we find it. If it's in the top half of the list, we're going to start at the other end. So that's just a way to do sequential search for our linked list here. So we either start at the beginning or the end, depending where the index is. And then we have our iterator, just like we did with our array list approach. So we still have an iterator method, and we have linked list iterator, which pretty much is the same thing as array list iterator, except a couple things. So like, for example, our current is not initialized to 0, it's initialized to begin marker.next. So that will give us the first node in the linked list. We have this expected mod counts and OK to remove. We'll talk more details about that in a little bit, but we use expected mod count to compare with mod count, such that if changes are made to the list, we need to make sure that our iterator is still valid. If we change the linked list, the iterator is not valid. So we use this expected mod count to see if the iterator is still valid. And then the OK remove is basically a Boolean variable that lets us know if we can remove a particular node after doing some stuff. So we still have hasNext, which just checks to see if we're at the end marker. We have our next method, which will check to see if the iterator is still valid. So that's what this comparison is doing. And if it's not valid, we'll throw an exception. We'll check to see if there is still an element or a node to go to. If not, we'll throw an exception. So if it's valid that we can go to another node, then that's what we'll do here. And we'll say it's OK to remove and return the value of that item. And then we have our remove method, which once again checks to make sure that we haven't made any other changes to the list, and we haven't already done some remove. If it's not OK to remove, then we need to say that it's not OK to remove. And then we call the appropriate remove method from the myLinkedList class. And then we would increment our expected mod count, because we made a change here that's also going to increment mod count. So this remove is okay, because we're calling remove here. It does not invalidate the iterator, so we can do that. And we'll say OK to remove is false, because we just removed something, so we need to call next before we can call remove again. And that is the complete implementation for the myLinkedList class.